Good morning. Today we will try to understand what is known as signal space representation of digital signals. In this course, so far what we have learnt is amplitude modulation, frequency modulation, in which the message signal exists in the analog form itself. So we resorted to modulation and it transmitted, and we understood the performance of these systems in presence of noise. Then we said that we pointed out certain drawbacks of such analog communication systems, and we said that digital communication method offers many advantages. So for which what we are supposed to do is, we have to convert the analog signal into digital, which we have not understood, studied in this particular course. We will perhaps do it in the next course. But there are certain sources which deliver digital information. For example, computer data. Computer data is by nature digital. It is a representation of alphanumeric characters and certain special characters. And what are the various ways of representing such characters or such symbols, etc. we have understood through certain coding schemes, what are known as source coding schemes, like the Huffman coding, Shanmugavel coding, and so on. So the output of such a coding scheme is binary digit. So message, you had a message which was giving you some, say, MI. Okay, these are message symbols, M1, M2, M3, M4, depending upon how many characters a particular source emits. Then now we are supposed to transmit these messages through transmission medium, for which we require a transmitter. Let us say this is the transmitter. Okay. Now, what does the transmitter transmit? We have to first of all show an electrical equivalent of this message. This message can be 1010 like this. So this could be, this MI could be 101110, something like this. But if you have to transmit through a transmission medium, we need to represent these messages in the form of electrical waveform. Okay? Let us say we represent these messages, each message, M1 as, say, some SI of t. Okay? M1 as S1 of t, M2 as S2 of t, and so on. Let us say there are some M symbols, capital M symbols, and we will say capital M waveforms. Corresponding to each distinct symbol, we will have to select a distinct waveform, time domain waveform, which can be represented as an electrical waveform and transmitted through the channel. Okay, that is a channel. Now we are talking about AWGN channel. Okay, AWGN channel. So at the receiver, you get x of t at the input of the receiver. This is received. Okay, and then you get some m hat of t. M hat. So an equal estimate of, this is an estimate of mi. Okay. So we have understood that using Huffman encoding and other encoding schemes, binary digits are generated, and these binary digits are transmitted through a channel. So we have two options here, either a baseband transmission or a band pass transmission. Okay. So in baseband transmission, what we will do is, we will represent each one of these distinct bits using a waveform. Okay, which is, whose spectrum is starting from 0. Which is so you have option here is baseband transmission, or band pass transmission. These two options we have. Now in baseband transmission, what we do is we represent each of these messages. The message could be bits, or it could be a group of messages, bits, and so on. So you will represent by a waveform. This will result in a waveform whose spectrum is like this, starting from 0. Okay, is somewhere something like this. Okay, this is spectrum. So you will use a waveform whose spectrum is of that nature. In band pass transmission, you will use a waveform whose spectrum is, this is 0, this is again 0. Spectrum is something like this. So some Fc minus Fc, let us say. So you have two options. Select a waveform here or select a waveform of this type, resulting in a spectrum like this, resulting in a spectrum like that. So whether we will choose baseband transmission or band pass transmission will depend upon what we require to do, what is our requirement. So we will not go into the details of these different types of waveform. Each one is a subject by itself, so is a chapter by itself. So we will not go into those details. But what I am trying to arrive at is that corresponding to each message, we need to select a waveform. This is what we have to understand for transmission purposes. Okay. Now, what type of waveforms will you select for transmitting these messages? Normally, the objective of a communication engineer in selecting waveforms is to select the set of waveforms for representing these message bits in such a way these waveforms will lend itself for optimum reception, optimum detection of the messages. So by which, what do we mean? We will understand as we proceed further, we will understand this optimum reception a little more. Now at the moment, we would like to emphasize the point that the selection of waveforms depends upon how these waveforms allow optimum reception of the signal at the output in presence of noise. Okay. So, now this representation of these signals can be visualized. Now this representation of waveforms can be visualized in time domain. Okay, in time domain. The waveform will look something like this, let us say. Okay, some waveform, just time domain, a waveform will look like this. In frequency domain, the same waveform. For making things clear, I will assume a sine wave here. In time domain, a sine wave of this nature. Okay, one frequency. In frequency domain, say let us say this is say this of 0. Okay, this is 0 and this is frequency axis. So this is the waveform having a frequency of 0. Okay, frequency of 0. So if you want to visualize this waveform in the time domain, it will look like it will running from minus infinity to plus infinity. Okay. the same waveform can be represented as one value at a particular frequency. The amplitude depends upon the amplitude of this waveform. So in other words, we are visualizing this waveform or representing this waveform in frequency domain as one value, one frequency and its amplitude. That's all. By representing like this, we get certain new revelations. Easy understanding of the waveform. We will come to that later. The Fourier transform, Fourier series and Fourier transform are such examples. Okay? So this is like this. You can also visualize this waveform in space domain. Now in space means this is here x-axis is the frequency, y-axis is the amplitude. Here x-axis is the time. Okay, this is x-axis is the time, y-axis is the amplitude. So amplitude here, this is amplitude. Okay. So in the space domain, we need to understand whether the signal that we are going to select is a one-dimensional signal, or a two-dimensional signal, or a three-dimensional, and what is the dimension of this. Depending upon the dimension, okay, you will represent, let us assume that it is a two-dimensional signal. That means this is some x-axis, this is y-axis. Okay? And if you want to represent this signal, you can represent this as one single point. Say one point, that's all. Okay? How to represent, we will see. So we can either represent like this in the time domain, or represent like this in the frequency domain, or you can represent in the space domain as one single point. Now, each of these representation will help us understand the signal better and better, and help us design the optimum reception so that we can deliver the signal at the output of the receiver with the less effect of the noise. Okay? So now let us see in general how we can represent the signals in the space. It's called a signal space representation. So you represent this signal in the space domain. So how do you do that? For which we need to understand certain mathematical approach of representing waveforms using what are known as orthogonal basis functions. Okay? Now let us try to present in a mathematical form the signals, and then we will try to understand what do these how many dimensions are required to represent these signals. Okay. Okay, now what I would like to point out here is, for 1 bit you may transmit one waveform, because here is a binary representation 1 and 0. So you require either, for binary representation, you require the 1 0, therefore you require S0 of t and S1 of t. Only these two waveforms are sufficient to represent binary. But in real life, you will understand it later when you come to know about digital modulation. There are certain advantages of grouping these binary bits into certain number of bits. For example, grouping this into three each, like this. This is 1, 3, and then let us say 1, 1, something like this. So like this. So if you have 3 each, group of 3 bits, So how many? This is called generally they call it as M-ary. Okay, binary M-ary. In the M-ary, M will always, the M is a power of 2. Okay. Now in this case the power is power of 3. Okay. If it is power of 3, 3 together. How many such possibilities are there? There are 8 possibilities. So M is equal to 8. In that case, you have 8 possibilities. S0, S0, S1, like this, S7. There are 8 possibilities. S0 will represent 0, 0, 0. S1 will represent 0, 0, 1. Like that, S7 will represent 1, 1, 1. So this way, we can represent the same binary information into certain blocks of symbols. Each symbol is represented by a waveform for certain it will result in certain advantages in the form of conserving the bandwidth or in the form of conserving power in the presence of white noise. So there are relative merits and demerits. We will not go into those details. But we are in general saying there could be some Si, it may be M can be any value. So M signals are required even for binary information like this. We will consider it to be a set of symbols. Therefore, M is more than 2. Okay, that will be decided by the requirement. Okay, so we will select like this. Now let us say, if we select these signals in such a way that each one can be represented as a linear combination of orthonormal functions, then it will result in optimum, it will help us designing optimum receiver. So let us now first understand that we can represent, say, some S1 of t. This is one waveform. Okay, this is S11 phi1 of t plus S12 phi2 of t plus S1 n phi n of t. So what we are saying, S1 of t is represented as a linear combination of phi 1 of t, phi 2 of t and phi n of t. These are the coefficients of each one of these. Similarly, S2 of t can be represented like this: S2 of 1 phi 1 of t plus S22 phi 2 of t and so on, S2n phi n of t. This way, the M signals, all the M signals can be represented like this: M1, like this, where this phi 1 of t, phi 2 of t, phi n of t are orthonormal basis functions. So, our objective is to select appropriate waveforms for transmitting these binary blocks of information. And we are saying we will select these waveforms S1 of t, S2 of t, S3 of t, Sm of t in such a way that they can be represented as a linear combination of phi 1 of t, phi 2 of t, phi n of t, where this set of functions are called orthonormal basis functions, because these functions will have the property that phi, say 1 square of t dt 0 to t is equal to 1. Similarly, any function phi j square of t dt is equal to 1. So all these functions are having unit energy. This is energy of the signal, energy, it is having unit energy, and all these functions are, say, some phi I into phi j t dt equal to, say, some delta ij is equal to 1 0 1 if I is equal to j, 0 I is not equal to j. So what are we saying? You will be given the notes properly. You must listen to this message matter, and then you will understand later. So we will select these waveforms in such a way is, if somebody tells you about this set of functions phi 1, phi 2, phi n, which are orthogonal to each other, that means any phi 1 of t, phi 2 to phi 2 of t, integrate over t. Now orthogonal means this t is the transmission duration. We are saying this is the symbol duration. Okay, whatever may be the rate at which you want to transmit. With 3 symbols means 3 into TB. 3 TB is 1 T. This is called duration T, duration T, duration T. So in that duration, these functions are all orthogonal to each other. 0 to T, if you integrate these two functions, it will result in, this is what is also Kronecker delta, which is equal to 1 if I equal to j. If I equal to j, it is energy is equal to 1. If I is not equal to j, they are different, output will be 0. So that means they are orthogonal. So all these functions are orthogonal to each other and they have unit energy. So if someone tells you or gives you a set of basis functions which are having unit energy and orthogonal to each other, we can represent our signals using those orthogonal functions. And what is the use of designing such waveforms? It must help us in certain form or the other. Then only there is a meaning in representing like this. Now suppose we select waveforms which lend themselves to be represented using a set of orthogonal functions. Then how does it help?